All right, Algebra 2. Getting into section 7.5 is when we start putting it all together and also realizing why we've been learning most of what we've been learning here at the end of chapter 7. We've spent 7.3 and 7.4 learning what a logarithm is and then what the properties of logarithms are and how that can be used. We're going to need a lot of those skills with what we're doing here today. So I want to remind you guys that pretty much the number one thing that we do in algebra, whether it's algebra 1 or algebra 2, is we solve equations. And in almost every chapter of Algebra 2, we're learning a new style of equation that we haven't dealt with before, and we're learning how to solve that. Well, now in 7.5, we get into two new types of equations, everybody: exponential equations and then logarithmic equations. And I know that some textbooks and some teachers kind of split this up and do exponential equations in one section and then logarithmic equations in another. We're going to go ahead and kind of just jump back and forth between the two of them here because I want you guys to be relatively fluent with that. They're certainly related to one another. All right, so let's take a look at our first example here where we've got 7 to the 3x minus 8 power is equal to 7 to the 19th. Okay, this right here, everybody, is what we call an exponential equation, and that's something that hopefully you've been getting a little bit familiar with throughout the course of this chapter. The reason this is an exponential equation is because it's an equation and the variable is located in the exponent. Guys, this is nothing that you saw in middle school, nothing that you saw in Algebra 1, and you haven't seen it up until right now, I don't think, in Algebra 2. So an exponential equation is one where the variable is in the exponent. And we've got to figure out a way to get the x, or x's, as it will be in later problems, down from the exponent level down into the base level, or the main level that we call it. Well, I'm starting you guys off with a really easy problem here, because what I want you guys to notice is you've got similar structures on both sides of this equation. 7 raised to a power is equal to 7 raised to another power. You've got the same base on both sides right here, and 7 to some power equals 7 again to some other power. Well, we know that this exponent right here is just 19. This one then, the 3x minus 8, and I end up writing pretty much the same thing I just had. What I'm hoping you guys notice, though, is this: if the bases are the same, what that means is that these exponents have to be the same. So I'm going to give you guys the real quick version of how to do this problem right here, everybody. In fact, let me just erase all of that junk and get right to it. If the bases are the same, then the exponents have to be the same as well. We'll set 3x minus 8 equal to the other exponent, which is 19, and just solve that. What I'm essentially saying, and I'll explain why this is the case in just a minute, you can basically just ignore the bases if they're the same on both sides. So what would we do here now, guys? We would add an 8 to both sides right here and get 3x is equal to 27. Divide both sides by 3, and we'll get x equals 9, and that's it. So that's how you solve a really simple exponential equation where you've got the same base on both sides. Now, technically, I said I would explain this. You guys can skip this if you want. Here's what we're actually doing. If we took a look, let me switch colors right here and go to green maybe. If we took 7 to the 3x minus 8 power is equal to, and I'm going to leave some room here, 7 to the 19th, what we can effectively do then, guys, is do a log on both sides of the equation. And as long as we do the same log base on both of them, we're fine. Well, the smartest thing to do here would be a log base 7. And if I do that on the left, I would do the exact same thing on the right. Now, there's a couple ways you can go from here, but what I would probably do is now try to apply the power property that says a log base 7 of 7 to a power, you can bring this exponent out in front as a coefficient. And I would do the exact same thing right here. So that now would get us 3x minus 8 times the log base 7 of 7 equals, we would now have a 19 out in front times the log base 7 of 7 as well. And what I'm hoping everybody's pretty familiar with now is log base 7 of 7 can be evaluated without a calculator. It's asking us 7 raised to what power is equal to 7? And the answer to that is 1. And of course, the exact same thing happens right here. Log base 7 of 7 is 1. So that now gives you 3x minus 8 times 1 is just itself equals 19 times 1, which is just 19. And now you'll see we are right where we were here a moment ago, everybody. And that's the reason why the bases, the 7s, cancel out, and you can just set power equal to power. Assuming, though, let me say this again, guys, that the bases are identical. If they're not, which they won't be in some future problems we're going to do here, then you have a whole other issue. But we'll worry about that when we get to it. Okay, so that's how you solve a really simple, straightforward exponential equation. Let's move on to problem number 2 here, everybody, which looks like this. And what I'm hoping you'll notice right away, this one here is not an exponential equation. This one is a log, I got to think about how to spell this, logarithmic equation right here. We've got logs on both sides. But I'm kind of hoping you get the joke here as well, everybody. A log base 3 on the left of something is equal to a log base 3 on the right of something. Okay, the short way to do it, you can just ignore the log base 3's on both sides and simply get 5x minus 1 is equal to x plus 7. Let me go ahead and finish this problem, again, doing it the quick way, and then we'll come back and talk about why it works. So I would just subtract an x from both sides and add a 1 on both sides at the same time. 5x minus x is 4x. Those cancel, those terms cancel, and 7 plus 1 is 8. Divide by the 4 and get x equals 2. And one thing you can always do, guys, when you're solving an equation to check your answer, plug it back in and make sure it works. If x is 2, 5 times 2 is 10, 10 minus 1 is 9, and this left side is now log base 3 of 9, which means 3 raised to what power is equal to 9? This whole left side then, guys, is 2, because 3 squared is equal to 9. Well, how about the right-hand side then? Again, if x is 2, 2 plus 7 is 9, and the right side is now asking you 3 to what power is equal to 9? That's going to be 2 as well. So that kind of verifies that this answer here is correct. Now, the real thing that we're doing, all right, let me see here. If we went back to the original statement right here of log base 3, of 5x minus 1, that would equal the log base 3 of x plus 7. What we're really doing here, guys, is exponentiating both sides with a base of 3. Again, I don't want to spend all day on this, but the 3 and the log base 3 cancel each other out, and that leaves you then with the 5x minus 1 equals, and then the x plus 7, which is right back to where we were. Most people are pretty comfortable shortcutting this problem, though, too. If you've got the same logarithm base on both sides, you can just ignore those logs and just say product on the left equals product on the right. And I've got one more problem for you guys that kind of, sort of, a little bit is in the easy category that we can work around with what we might call common sense. Although I know people hate it when a math teacher says something like that. It's not necessarily common for everybody. So let's talk about this problem. Number 3 is an exponential equation. We've got 4 to the 3x power is equal to 8 to the x plus 1. Now, this looks more like example 1 we just did rather than example 2, but what made example 1 really easy is the fact that we had the same base on both sides. So we could just ignore the 7s and just say that the two powers had to be equal to each other. No such luck right here. 4 and 8 are obviously not the same number. However, they do have something important in common, and we're going to take advantage of that right here, guys, that 4 and 8 are both powers of 2. That means that we can rewrite the bases here in terms of 2 raised to a power. The 4 right here could be written as 2 squared, and that's still being taken to the 3x power. Equals, here we go, the 8 here on the right is 2 to the 3rd power, and that's still being taken to the x plus 1 power. And what have we just accomplished now? Well, a power of a power, this is when you multiply your exponents together. So this is going to be 2, and the power now is going to be 2 times 3x, which is 6x, equals 2 over here, and a monomial times a binomial, that's when we have to distribute. This is 2 to the 3x plus 3 power. And now, you guys, right here, this becomes a problem just like number 1. Since we've got 2 to a power equals 2 to another power, you can just ignore the bases of 2 and set the powers equal to each other. 6x has to equal 3x plus 3. So I'll subtract this 3x from both sides right here. 6x minus 3x is 3x. Those terms are gone, and I get a 3 there. We'll divide by 3, and we'll get this nice solution of x is equal to 1. And again, guys, always a good idea to check your answer by plugging that value for x back in. 3 times 1 is 3, so now 4 to the third power should be equal to 8 to the 1 plus 1, 8 to the second power. Well, 4 cubed, 4 times 4 is 16, times another 4 is 64. 8 squared, of course, is 64 as well. So I'll put a big check mark by that one. Once I verified that, I feel pretty confident then that this is the right answer here for problem number 3. So that's definitely tougher than what we did in number 1, but we still were able to get to the same spot. But the plot thickens, if I recall here, everybody, as we get to problem number 4. 2 to the x is equal to 7. Now, what I'm hoping you guys recognize relatively early on is that while the statement here is relatively straightforward and simple to grasp, the answer is not. I'm hoping everybody can tell me right now that 2 to the first is 2, that 2 squared is 4, and that 2 to the third power is equal to 8. None of those numbers, you will notice, guys, is 7. And there's really not any point in going further because we already hit 8, which is bigger than 7. So there is an answer to this question. 2 to what power is equal to 7, but it's not going to be a rational number. I know that my answer is going to be somewhere between 2 and 3. And if I had to guess, since 7 is closer to 8 than it is to 4, I'm guessing the answer is going to be closer to 3 than it is to 2. But that doesn't really help us find that answer. So what I'm going to talk to you guys about right now is a concept that I really find helpful anytime you're solving an equation here in Chapter 7 and you feel like you're kind of at a dead end right here. What we're going to do instead, let me use the word right here, everybody, is translate. Now, this is something we've spent some time doing within the last week or so, really at the beginning of section 7.3. When we first learned what a logarithm was, the first problems we dealt with there, guys, whether it was in our notes or probably on your homework, was translating back and forth between exponential statements and logarithmic statements. And what we have right here given to us, guys, is an exponential equation. 2 raised to the x power is equal to 7. We have a base of 2, a power of x, and a product of 7. So let's translate that into a logarithm. It's going to be a logarithm of what base? Well, the base of your logarithm is the same as the base of your exponent, so it's going to be log base 2. Then the number that comes after that is the product now, and the product of this exponent right here was 7. So log base 2 of 7 equals, and the number that comes over here, guys, all by itself as the answer to a logarithm is the exponent here. That is where the x goes. So we've translated the exponential statement, 2 to the x power equals 7, into the logarithmic statement, log base 2 of 7 is equal to x. And we've accomplished 2 really important things by doing that, guys. Number 1, we've taken the x out of the exponent where we didn't really know what to do with it, and we've moved it down here to the base level. The second thing we did, which is probably less important now, the x is already isolated. All we have to do, you guys, is go to our calculator and ask it, what is the log base 2 of 7? And that is going to be our answer. So unfortunately, guys, I've got to use this calculator, which is different than the one that you guys are using, but it gets all the same information across here. So for you guys on the 84, I'm looking at mine here, you've got to hit you've got to hit alpha, F2, and then number 5. For me, I think I just need to hit this log button right here. And we wanted to know what is the log base 2 of 7. So I have to do this, and there you go, guys. Now, we said it was going to be an irrational number. Looks like it is. between 2 and 3, definitely, and we thought it was going to be closer to 3 than it is to 2, and I think we've got it right. Follow the directions for whatever it says, you guys, on your homework or your quiz or your test, but very often with logarithmic problems like this, we round our answers to 4 decimal places. So this one is going to be 2.8074. So let me write that down. 2.8074, and that should be it. Now, always a good habit to get into of checking our answer. 2 to this power of 2.8074 should get us an answer of 7. So whether you're using my calculator or yours, we're going to hit 2, then the exponent button. But guys, rather than hitting or typing in 2.8074, you guys on your calculator are going to hit second and then the negative key, which will get an ANS to get brought up right here. And for me, I do it that way. 2 to the previous answer power should get us that answer of 7. And sure enough, there you go. So now we know that we got that answer right. And this is our correct answer here for problem number 4. So I'll reiterate here, guys, whenever you're stuck, translating is very often going to get you in a different form, just allows you to look at the equation in a different way, and very often then that is going to give you the solution. So I want you guys to make a big stink about this in your notes right here. When you're stuck, translate from exponents into logs, or maybe, I think we'll get to this a little later, from logs into exponents. Okay, moving right along, let's take a look at example 5. And it may not look like it, but example 5 is really similar to what we just did in example number 4. We have an exponential equation, meaning that the variable is located in the exponent. So what are we going to do? Well, first of all, we need to isolate the base to this power right here. We need to get this term all by itself, which we're going to do first by subtracting a 4 from both sides. And that'll give us 10 to the 2x minus 3 power is equal to, and that 21 minus 4 is going to be a 17. Now, there's a couple of different ways of explaining what to do next, but I want to try to be consistent with you guys, and why did I space that out so much? And I want to use the little hint I just gave you guys. We can't do anything else right here to get the x by itself here. We've simplified that left side as much as we can, so I would translate now from exponents into logarithms. I would rewrite this as a log in what base? Remember, the base of your logarithm is the same as the base of your exponent, so that's log base 10. Then, after that, the product comes next, 17. So it's log base 10 of 17 equals, and the answer to a logarithm is the power, 2x minus 3. So this one isn't quite as clean as the previous problem. I've still got work to do over there on the right-hand side to get x by itself, but for the most part, I think you can see what's going on. Now, before I go to the calculator, I'd start doing work by hand. I'd add 3 on both sides right here. Those are going to cancel out. And what you want to be careful not to do, you guys, is this. Do not write this as log base 10 of 20. It's not like there are parentheses here that we just crammed in. If anything, really, it's like there's parentheses here. So this is absolutely not the way to go. Probably the best thing would have been to write this as 3. Put that out in front, plus the log base 10 of 17, all of which would equal 2x. And now we're just about done. We need to divide the right side by 2, and that means we need to divide the entire left side by 2 as well. Those 2's are going to cancel, and this then, everybody, is going to be our answer. We're going to get x equals this whole quantity right here, which we should be able to put into the calculator in one step. So I really don't need the brackets right there, but what do we got? 3 plus, all right, log base 10 of 17. I'm going to go with a stacked fraction and make that 3 plus, here we go. And then it was log base 10, although remember guys, you really just could hit your log button right there. You don't need to type in log of base 10. That's the common logarithm. Okay, and I believe that was all over 2 if I'm not mistaken. Yeah, all right. So whoa. There we go. So let's put a 2 right there. And here we go, guys. We should get an answer now. That's not what I wanted. This is what I wanted. There you go. Should get an answer of 2.1152 if we're rounding to the nearest 10,000th. 2.1152. Now, how could we make sure that we are right? Especially if you've got a little bit of extra time here, everybody, before you turn in your quiz or your test. You should always go back and check these answers. Let's take that value for x and type it into this expression right here. And when we hit enter then, we should get 21 for our answer. So 10 to the 2x minus 3 and then a plus 4. So 10 to a power, and that power was going to be 2x minus 3. Did I do that right? Yeah, 2x minus 3. Okay, gotcha. So where were we, guys? So it would be 2, and then multiplied by the previous answer. Okay, so 2x minus 3, get out of your exponent, and then do a plus 4 at the end of all that. And when we hit that answer then, guys, we end up with 21, and I believe that's exactly what we were going for here. So now we have verified this answer right here, and we know that this one is correct. Okay, so that's kind of how things are moving along, sir, so far, guys. So number 4 was kind of a simple but irrational answer here for an exponential equation, and number 5 is a little bit more complicated, but the same basic idea. Okay, so let's shift gears again now, guys. Let's go back to solving a logarithmic equation. The log base 5 now of 3x plus 1 is equal to 2. So the question becomes here, everybody, how do we get rid of this logarithm? And again, there's multiple ways of explaining it, but what I like to do is when I'm stuck, I always like to translate. Now, in the last two problems, we've translated from an exponent into a logarithm. Okay, and now we're going the other direction. We're going from a logarithmic expression, actually all of that, a logarithmic equation into an exponential equation. So what's the base of this exponent going to be? The same as the base of the logarithm, which is 5. It gets taken then to this power right here, 5 squared, and it equals this number right here, which is your product, 3x plus 1. If you guys are fluent at translating back and forth between exponents and logarithms, then most of these problems are pretty straightforward. You're just changing from one form into the other. If you take a look at what we have written right here, guys, my x is down on the main level, and I don't think anything here looks difficult to solve. I'd evaluate the 5 squared first to get 25 is equal to 3x plus 1, and this is an algebra 1 equation. I'd subtract 1 from both sides to get 24 equals 3x, and then we would divide by 3 to get x equals 8. And I think that's all she wrote. Let's try it, guys. 3 times 8 is 24. 24 plus 1 is 25. So the log base 5 of 25 should equal 2. Does it? Does this base raised to this power equal this product? Absolutely. 5 squared is equal to 25, so this answer is verified there as well. So if it looks to you guys like we're just kicking butt and going through these problems in the middle pretty quickly and pretty easily, yeah, we kind of are if you master this concept here of translation between logarithms and exponents. All right, moving right along, the plot's going to thicken a little bit right now. So here I was just saying all this was going pretty quickly. Yeah, problem 7 is a tougher one. For the very first time now, guys, out of all these problems, we're seeing an expression that has 2 logarithms in it. And we haven't talked about how to handle that at all. So what we're going to try to do is condense. There's a word that we talked about in section 7.4, everybody, and condense means to take an expression, like your left side here, that's written in terms of 2 logarithms and condense it down to just 1. We would like to write this left side as a single logarithm, and we can do that using the product property. So what you guys wrote down in 7.4, let's see if I remember the exact wording here, is the log base A of B, well, you wrote it this way. The log base A of BC can be broken down into the log base A of B plus the log base A of C. And I really am reading this property backwards here. We start off with 2 different logs, but in the same base being added together just like we had right here. And we can write that then as 1 logarithm, but then we multiply the B and the C together. So that means, guys, that a log of 5x plus a log of x minus 1 becomes a log of 5x multiplied now by x minus 1. And I need parentheses around that x minus 1 because it's a binomial, all of which equals 2. Well, let's do a little work right here, guys. A monomial times a binomial, this is when we distribute. So this now becomes the log of, oh boy, 5x times x is 5x squared, and then a 5x times minus 1 is a minus 5x. And all of that is equal to 2. Okay, so with all that in mind, I don't know that there's anything else I can do to simplify this, so now I'm going to translate again. I'm going to translate this into an exponent. What base? Well, it's the base of the logarithm right here, and when there is no number there, that's base 10. We take this base raised to this power, so 10 squared equals this product right here, which is 5x squared minus 5x. And now if you'll notice, guys, there's no more logarithms right here, but what we are dealing with, I believe here, is a quadratic equation. That 10 squared is going to become 100, and I'm going to bring that over here to this side. So I'm going to get 0 equals 5x squared minus 5x, and this 100 we subtract and get a minus 100 at the end of that. And of course, the first thing I try to do in solving any quadratic is factoring. And the first type of factoring we always look for is GCF, monomial factoring. And here we can pull out a 5. That'll leave us with an x squared minus x minus 20. Now we work on this quadratic trinomial. And I like the looks of this, guys. I think it's going to factor. What times what is x squared? That'll be x times x. This symbol right here tells us if the signs are the same or different. Since it's a minus, that means the signs are different. One here is a plus, one here is a minus. And now we need two numbers that multiply to negative 20 and add or combine to negative 1. Those two numbers are going to be negative 5 and positive 4. So you're welcome to check this if you guys would like with FOIL, but yeah, sure enough, this product right here is going to get you right back up to where we were just a second ago. Okay, so we're making good progress here, guys. Now what? Now you take each of your three factors, set them equal to 0, and solve. Well, this is kind of silly. You can't solve 5 equals 0 because 5 doesn't equal 0, and it never will. It's a constant, so you can just ignore that. But from here, you're going to get x equals negative 4, and from here, you're going to get x equals 5. So it certainly looks like there are two solutions to this equation here. But unfortunately, you guys, you do have to pay attention right here to reality, I guess. One of these solutions very often ends up not quite working out, and I believe that's the case right here. I'm going to go ahead and move this equation all the way down here. Let me slide things up just a little bit. Okay, so let's take a look here at each of these answers here and see if they work out or not. So I'm going to switch to green, and let's try negative 4 first. This now becomes the log of 5 times negative 4 is negative 20, and I'm going to stop you right there. Log of negative 20. Remember, this is log base 10. So what they're asking us here, guys, is 10 raised to what power is equal to negative 20. And what we have here, you guys, is an impossibility. You cannot take a positive base like 10 to any power and get a negative result. A positive number to any power will always be positive. So that tells me right there, negative 4 doesn't work, and we have to throw it out. The name for that, not really important that you guys write this down, is called an extraneous solution. An extraneous solution is one that looked like it was going to work algebraically, but then when you put it back in, it just didn't pan out. Okay, how about the second solution then? We should not assume that the second one is going to work just because the first one didn't. So let's see if we run what happens now. If x is 5, 5 times 5, okay, we get the log of 25. And then plus the log of 5 minus 1 is 4. Gotcha. That should equal 2. Well, I could do this a couple of different ways. What you guys would probably prefer the most, I think, is typing it into your calculator. Log of 25 plus log of 4. So log, I'm just going to ignore the base right there of 25. You guys can just use the log key on your calculator. And then plus the log, again, skip the base of 4. Oh, wait a minute. That is not what I wanted to do. Sorry about that, guys. I typed that in incorrectly. So log of 25, get out of there, and then add to that the log, skip the base, and put a 4 right there. Okay, that's what I was expecting. Now I typed it in correctly. We ended up with 2 for our answer, which is exactly what we were hoping to see for that right-hand side. You could have also realized that you can use, kind of like we did before, the product property to combine these two logs. This becomes the log of 25 times 4. Does that equal 2? Let's see. This is the log of 100 equals 2. And remember that log without a base means base 10. Is it true, everybody, that 10 raised to the second power is equal to this number here? Yep, that one works out, so I feel pretty darn good about x equals 5 as a solution. But we found an extraneous, and we had to throw that one out. So there really is only one answer here to this problem, and it's x equals 5. All right, guys, that is 7 good problems right there. I'm going to stop this video. We'll upload this one. Then I'm going to come back and do the last 3 problems in a second video because those last 3 are going to take a little bit longer. So hopefully that's a good start to get you guys rolling on your homework on 7.5, but make sure you come back and watch the last few examples in the next video.